Hello, here, Prox Mathematics here, and let's get to the problem. Okay, this was actually sourced from myself. I thought it on my own. So, point P is randomly chosen in this tetrahedron. What's the probability that P is closer to its center than any of the vertices? So, if we choose a point P, we want it to be closer to O than A, B, C, and D. Yeah, A, B, C, D. So it must be closer to O than any of them. And you first might think this would be a sphere, but if you draw a sphere from these two, there would be a lot of empty space in between. So let's draw the midpoint. Make a very crucial observation. And if we extend this bisector to the tetrahedron, then it actually intersects it with a plane. And this one, this tetrahedron formed here, is similar to the original tetrahedron. Right, so we have that these two are equal. I'm gonna mark this with blue. These two are equal. And if we actually chose a point anywhere on this plane, like here, and we connected it here to find the distances, these two are equal, right? And if we draw one through the bisector plane, it would intersect at a right angle. Then this length is equal to itself, the short leg which goes through the plane. That means these two lengths are equal because they're hypotenuses of congruent triangles. Got it? That means if we choose any point anywhere on this side of the plane, then it would be closer to O than A. But we also don't want it to be closer to B or C, especially B and D. Let's see. What if we make a similar tetrahedron that passes through O? One like this. Now, can we guarantee that it's not closer to D? Let's see. If it's on this side, it would be closer. Actually, let's do the same thing for E, for example, and bisect it. Let's see the tetrahedron that forms. So if it's anywhere on the side, it's going to be closer to O than B, the point P. Okay, so how do we relate the tetrahedron on A and the one on B? Let's see. Actually, we're lucky that there's a lot of empty space here, because now if it's anywhere over here, it's going to be closer to A than both A and B. So closer to O than both A and B, since the space does not lie in A's or B's territory. Let's call it territory. Okay. So the same goes for C and D. You can draw tetrahedrons, but how do we know that these two tetrahedrons don't intersect? It's actually a clever way to find out. Now drop an altitude from O. So since this is a regular tetrahedron, the only place it could hit would be the center of triangle ABC. Yeah, since it's center. Okay, so, and since this is an equilateral triangle ABC, this point, this length over here, this length over here would be 1/3 of the total median from A to BC. So you can call that length X, and this length is 2x. Basically what I'm trying to say is that where point O drops in altitude to triangle ABC is 1/3 of the way from BC to A, or 2/3 from A to BC. That means if we draw a tetrahedron that passes through O, then it would be, sorry, well, let's say we drew one that passes through O. Then it would be 2/3 of the way from A to D by similarity. And since this tetrahedron is marked by the midpoint from O to A, these two would be equal. This is 1/3 of the way. That means all these three lengths would be equal, since they're all 1/3 AD. And since it's a probability problem, we can just make 81. Right. So next, you probably just have to find the volume that's not inside any of the territories and just inside the entire tetrahedron. And from that now, we would have 1 minus, since there's 4 vertices, 4 times, since these are similar to the original tetrahedron, you can just use volume similarity, and this is 1/3 of the total length. So its volume is going to be 1/3 cubed of the total volume. And that's going to be 27 over 27 minus 4 over 27 is equal to 23 over 27. And that's our answer.